Uh, my name is Oscar Pinto. I'm a principal engineer at Samsung Semiconductor. Today I'm going to talk about computational storage programming. Um, it's the last session of the day. How many of you all have not attended the previous two computational storage sessions? I can pace my talk accordingly. Okay, there was one. All right. Um, so in today's agenda, we will cover, I'll give you a brief overview of the work we are doing. I'll touch on the programming usage. We'll use an example and we'll walk through the actual APIs and how they could be used. And I'll also provide a specification update from the API side, and we'll conclude following that. So why are we doing computational storage APIs? Now, we do know that there are different forms of compute that have been there for a while. There have also been computational storage by itself in different forms. The previous ones that the different forms of compute and the usages are more tailored towards more vertical stacks in the sense that the standardization is very different there. That is one. The second is the use of storage is not part of it, and most of them are compute memory-centric solutions. In SNIA, which is what I'm covering here, we defined different device usages wherein what we called as CSP, computational storage processor, computational storage drive, and arrays. And with that, we also brought in storage to be part of it, wherein you could use the benefit of peer-to-peer, peer-to-peer, where the data doesn't traverse the fabric, the PCI or the network fabric. So you get the benefit of conserving on your bandwidth while getting the maximum usage of your device. With the APIs, we take that into consideration that P2P is one of it. Plus, you get APIs that are highly abstracted but also simplified in a way that you could use them with different types of devices. So on the right, you have the stack that shows, so on the bottom you have the computational storage drive that is shown here, which has a storage, it has some device memory, and it has the computational storage resources, which we'll touch on briefly. Now, the device is connected to using some type of device driver. So we touched on NVMe in the previous session. So this would, if it is NVMe device, it would be an NVMe driver. But if it is some other device like an FPGA or something of that nature, you would have an FPGA specific device there. And as we go further up the stack, you have something that is shown as plugin. So this is basically the glue that connects the APIs to a specific implementation of computational storage. By doing so, you can practically connect different types of devices to these abstracted APIs. And that's what we mean by one set of APIs for different types of devices. And the specific device details can get hidden by doing so. So your actual hardware implementation, be it more generalized or vendor specific, can still be considered because the APIs would, the abstracted APIs would be connected in a way that you would hide these very specific details. Another benefit that you get out of this is you don't need to know about each device because the APIs underneath the covers will manage those specific implementations through whatever device driver and the plugin that it attaches to. So by doing so, you can abstract how the device is discovered, how the device could be accessed once it's discovered, and how the device's memory, how it is structured, whether it is mapped device memory, that is, it is visible in the host address space, or it is unmapped, like we previously touched on the NVMe session, where that SLM is not visible in host address space. And then take the benefit of P2P, the near storage access, and copy from that device memory to host memory. As we know, each device that comes with its own memory may have its own implementation of a DMA, so to say. And that is more optimal when done from the device versus done from the host. So for that, you have copy services or copy APIs that help you manage that data back and forth. You also have the CSFs, or the computational storage functions that run on your device that could be either downloaded or it could be configured so that you could run them. So the little box on the right, on the utmost right, is basically a set of CSFs that are shown here. These are not very specific to what SNIA is recommending, but these are very generic, that is used in today's use cases, wherein you have compression, decompression, encryption, checksum, and some type of database search, and so forth. And below that, we also show it could be a software-based or it could be a hardware-based function. It may be defined in an ASIC and so forth. And so that is as far as the CSFs go. And once they're downloaded, you would want to execute them. You may also want to configure them. That comes under device management and the overall mechanism to manage your device. So this is a broad usage of what the APIs can do. That is, with an abstracted interface, you can manage your device and also run functions on your device and basically compute. So with that, let's get down to the programming usage by itself. So we define two programming modes. One is privilege mode, wherein it's more of an administrative mode where you can actually configure your CSRs or computational storage resources. You could download CSFs, and you could configure them, and you can overall manage the device. So these type of operations are more tailored to an administrative type of capability. And then you have non-privileged operations, which is for the normal user, where you do everything else, which is discovery of your, starting with the discovery of your CSX, that is your computational storage device, your functions that are there on that device, then the memory and the allocation of that memory, and execution of CSFs, and also transferring data that is there on the device memory to host memory and so forth. So this broadly covers what you can do as a non-privileged user. So again, two programming modes, privileged and non-privileged. We will touch on the non-privileged mode operations. So let's walk through this example. Now this is not, we've used an example here that probably is compression, but it need not be. It could be anything. This is very generic. On the right, we have a figure with six, usages of that correspond to how we go about doing those 6 steps. So the first one would be, as shown here, we go around discovering your device, discovering your CSF, allocating some memory on the device, loading some data from storage into the device memory or FDM, and then running the CSF or executing the CSF on the data that was loaded, and then copying these results back to the host. So let's walk through each of the steps. So the first one, like I said, is discovery of the device. The second one would be discovery of the CSF. And the third one is allocation of device memory. And once you have done this, your setup is ready. These are the first 3 steps that you use for setting up this example. So with discovery of the CSX, what would you have an API that given the device path or a file or a directory. So from an application perspective, you're more used to knowing a device by /dev/NVMe 0N1, something of that nature. So if that is your usage, then you can provide that as your information, or it is a specific file at a specific path on which you want to do compute or a directory and so forth. So you can provide that as input, and given that input, you can find out which is your computational storage device. So that is one way of doing it. So once you do that, you get to know which is your computational storage device. Now, if you already know that, you can skip that step and go to the next step, which is get access to the device. And in this step, you would use that OpenCSX as the function. And given that the input that you got back from the previous API, you would go and access the device. Now, once you access the device, you get a handle to the device, and you use that handle for all other operations as the APIs are defined. So this covers the first step of discovering and accessing your device. So next one is you need to discover your function. So at SNIA, the way we define the APIs is we define the movement of data and the usage of it based on a function. And the reason we did that is from an application user's perspective, you're more interested in your application running or your function running, right? So everything is centered around the function. So what we did was we centered the usage of computational storage around the CSF. So when you discover your CSF, what you get back is you get back information on how that CSF or which is the memory that CSF has access to. If there are more than one function of the one that you requested, then it will provide you more than one, it will return more than one CSFs back. And this could be true if you had more than one implementation. Let's say you have a fast implementation in hardware and you have a soft implementation in software. So one could be performant but takes more power. The other one could be less performant but it uses less power. And it totally depends on the usage, that certain applications may want to use less power, certain applications may want more performance. So you have that flexibility. And when you discover your CSF, you get the information that says it is relative performance, relative power, and number of instances of this CSF that is available, and the FDMs accessible. And I'll get to that in the next slide. So basically, what you get is this CSF has access to all these FDMs, and this is no different than what we touched in the NVMe section, which was the reachability. If those who were there in the previous section, this is how we connect them. And what you do once you discover your CSF is you will pick the one that is, if there's more than one available, you'll pick the one that is most applicable to your usage. So be it for performance or be it for power. So once you've picked your CSF, you will walk that same list and pick up the FDM that you want to use. Now, FDMs could be located in a way that they may be near to that compute or maybe further away. So you need to see what works well for you. So it's possible that you're running this particular CSF and the output of that goes to the next CSF. And if that is the case, you need to make sure you pick up the FDM that is favorable to both these CSFs or these functions running. So you pick up, if there's more than one available, you pick up the FDM that is right for you and that is accessible by a compute flow. And while you allocate, you can specify whether that memory needs to be pre-initialized. So you don't need to go and do the equivalent mem set on that device memory because that API will do it for you. And in certain instances or certain devices, they may provide that capability of mapping that memory into host address space when you allocate it. So this is similar to, let's say your device comes with some memory and some of the FPGA GPUs already have that capability where your memory gets mapped into your host address space and then you use it as a virtual address. So if your device has that capability, this one API does that for you. Now let's look at that setup code, those 3 steps we walked earlier. So first we have the get CSX from path, which is here. And then you go along and open the CSX. The second one you do is get your CSF, which is get CSF ID. So here we provide the name of the CSF or we provide the global identifier, which again, I think we touched on in the last sessions. So you can provide the global identifier, or you can provide the name, and it will go and find out all the functions that closely match the requested function. And you get a list of functions with a count and the number in them, the length of it. So once you have that, you would walk that list and find out the one that is most usable by your function that you're going to execute. Here it is showing you the most performant one, but you could pick the one that is using the least power if needed. So once you have picked your CSF, next you would do is go and pick up your FDM or allocate some memory, and you would make sure that the relative performance of that memory is the highest, that it doesn't have many hops. It's not far away, but it is as close to your function as much as possible. Once you have that, you would get the ID to that memory and then allocate some memory. And you could also set up that memory in a way that it may be cleared. So here we're not saying clear. So for flags, we're giving it as 0. So this is all it takes. This is all the code it takes to set up the device to run computational storage. So you have accessed the device, you have accessed the computational storage function, and you also allocated memory. Now the third step, you may allocate it multiple times because you need an input buffer, an output buffer. You may need more than one buffer depending on what type of program or a CSF function that you're running on the device. So next stage is once you're set up, once you're complete your setup, now you're ready to run. And in that run stage, you want to load the data that you want to do compute on. And once you've loaded the data you want to do compute on, you would then next go and execute your function on the data that was loaded. And then once that execution is done, in this example, you would copy those results back to host memory. And that's all there is. So 3 steps for setup and 3 steps for run. So let's look at how loading storage data works. So as shown here, the loading of storage data it takes advantage of your peer-to-peer access. That is, data goes from the storage part of your device to the memory or FDM without leaving the device. Now, this is the benefit of doing computational storage, where data is loaded directly within the device and you save on your fabric's bandwidth. Now, loading of data could be done using a set of LBA ranges, if you know the ranges, or you could provide a file handle and an offset if you're using a file system and you have accessed that file in a way that it could be used for direct load and store operations internal to the device. So once you have loaded the device with the data, you could run compute. Now, the next 3 APIs, they follow a completion usage. It gives you 3 different options on how you can complete these APIs. So these APIs could be run synchronously, that is blocking, or they could be run asynchronously, either by using a callback or an event model. And you have this usage to make it very flexible that depending on what your usage is, you can apply it in your environment. So once you have loaded your data, the next thing you would do is you would execute that CSF that you got access to on the data that was loaded. So for that, you would provide that CSF ID which you had done as part of your setup, wherein you got your CSF ID information. You would provide the parameters that are required for that CSF. Now, depending on what function that you're running on the device, they may come with their own types of parameters, the input and output parameters that are needed for it. So you would provide that to that CSF that is going to be executed. And again, each of these CSFs, each of these APIs that are used in run have their own completion options, like I touched on earlier. That is, you can run them in synchronous or asynchronous mode. So once you have set them up for to execute that function, and it completes, next thing you want to do is you want to copy the results which are still on the device. You want to copy them back to the host, and this is the DMA operation, for which you have the copy function, which is the copy API shown there, queue copy mem request, where you provide your source and destination. So here the source would be FDM, and the destination would be host memory. And you would execute this copy mem request API. Now, again, this API too supports synchronous as well as asynchronous operations. As shown in all these three APIs, they have the synchronous and asynchronous approach, which means you can queue this, you can queue data to each of these APIs, and you can expect them to work either in synchronous or asynchronous mode. So once you have copied your results, you have basically used the 6 steps to do computational storage. So here is the total code that is required to do the run, which is load data on the device, run the function on the device, on the data that was loaded, and lastly, copy the data copy the results that was the output of the function that was run on the device. This is all the code that is really required. I know it's a little small, but that's it. I mean, the previous one was the setup, and this was the run. And here, as you can see, this is, if you're using the synchronous or asynchronous mode, the 3 modes of completions, you would specify, if you're running in synchronous, you wouldn't specify the callback or the event parameter. If you want the asynchronous callback model, you would provide a callback and not provide the event parameter. And if you want the event-based model, asynchronous completion model, you would just provide the event parameter. So to summarize, the run just takes these 3 steps, and setup, like I shown earlier, takes 3 steps. So 6 steps to use computational storage or the APIs, and that's all it takes to use a computational storage enabled device with the SNIA CS APIs. Yeah, only 6 steps, that's it. All right, so let me provide kind of a specification update from slightly different from what was provided early here. So this year we did a lot of changes that brought in additional features, like we included LBA ranges. So previously we just had an LBA and a set of blocks as input, but now you can specify a set of LBA ranges as input, because data could be scattered, and with large data that is being used for different use cases, this may be the case. So it takes input of multiple LBA ranges. And like I'd already said previously, that it can also take file input, which if you are using files, which may be the case with most usages, that you're using a file system for your data. So you could use your file and offset also as input. But in this update, we added this. We also added device memory usage, wherein you could have multiple device memory pools. So this was to include what was defined in NVMe and also the reachability concepts of NVMe. We also added initialization options to that memory, so you don't need to have another API go out and then initialize that memory. It also provided some of those safeguarding features that when you free memory, you can also initialize the memory when it goes back to the pool and so forth. We added a new concept called canceling IOs, wherein every time you queue a request, a compute request, let's say it didn't complete for some reason. So we added this concept of canceling that I/O or aborting that I/O. Now, from the API perspective, we have that functionality in place. Now, it may not be fully connected with the Linux subsystem. We are working on that, on how it can map to the lower layers and how you can cancel an individual I/O right from user space once it is queued. But that is a separate effort outside what we are doing in SNIA. But from the SNIA perspective, we have defined API to cancel an I/O that is outstanding. And also the global identifiers, which is you can identify a function either by a name or by a globally registered identifier, be it a specific checksum type or a compression type, and so forth. And lastly, we added basically the NVMe support, and some of these are the ones we touched on earlier, was NVMe support, but there are other subtle things that made it fully compatible with what we have defined on the NVMe side. And we also had configuration and download, the way we do it, updates to it, so it closely matches with what is done with NVMe, but also kept it as abstracted as possible so it is extensible for other interfaces. From the specification perspective, we are at 0.9 R1 as a release. It is out publicly available since end of July, and it is under membership vote, and hopefully we will have this as a standard in October sometime. So that's as far as the specification update goes. With that, I'd like to conclude that the way compute is growing, I mean, there is definition of how hardware is used today, because your central CPU is not capable enough to handle all that workload. And to that, there is new hardware and new ways being defined on how you can get to your data and run compute on your data. Computational storage and the APIs provide a means to that. That is, you can build solutions with the definitions that we have defined in SNIA today. And the API specification is kind of completed, is 0.9, and we are ready to get it to a standard. As we touched on earlier, it is a simplified model. Like I said, we just had 6 APIs. If you want to run it as a regular user, not many steps, and you can compare that directly with, let's say, another standard that may have 90 APIs, but here we don't have that many APIs. But it does the same functionality, it meets the same objectives. And plus it is extensible for different future memory usages, future data movement usages, and so forth. So we're looking at how we can extend it to new usages. It addresses the current NVMe computational storage architecture and minimum steps to adopt. I'm touching on that again, but that's really what it is. With that, okay, I do have some backup slides. Yeah, so this is the complete code we touched in 6 steps. It's really, really small text, but you could look at it maybe when you can download these slides later on. So please rate my session. That's all I had. I think I completed earlier than what my time was allocated, but yeah, I can take questions. Sure.
As you were working on the APIs, laying those proposals, do you have an internal process of validating the ideas and verifying that the APIs you are about to introduce, the way developers will use them, are actually convenient and will solve practical problems?
Okay, so the question was there a process that we used when we developed the APIs that touched on the developers as well as how they were to be used? Yeah. So the answer is yes, because as we developed the standard, we had industry leaders, vendors, and others get together, and we had from different factions of people actually building computational storage devices. And didn't happen in a day or two. I mean, we took close to since 2019. I shouldn't put a time on it, but yeah, we started somewhere around 2019, and we had some downtime. But yeah, we worked through many developers, many feedbacks, many public reviews, and what came out of that is the APIs. Yeah. Yeah. Thank you. Yeah. Hi.
Do you have any available prototyping simulation infrastructure, or when is that going to be available?
It's a good question. So, from SNIA perspective, I'm not supposed to touch on vendor-specific implementations or vendor, sample stacks and so forth. But there is more than one out there. Maybe we can talk offline. And yeah.
Are there examples of other sort of implementations of the specification besides the NVMe one?
Okay. Okay, so the question is, are there other implementations of this out there? Not that we know of, because I think we had quite a few different factions of the industry come together. We had 58 or something of that nature, many companies that came together to make this happen. Yeah, so I don't think so there's something separate. Now, there are...
Sorry, I don't mean from the SNIA spec, but from the NVMe implementation. Is the spec, the spec is designed to be more general. Are there other implementations of that spec, like perhaps in lower spec versions or in specific vendor implementations?
Yeah, so other than NVMe, you said, right? Yeah. So they could be, but I'm not aware of something of that nature, yeah. But even within NVMe, right? So NVMe has defined a path to how to access the device, how to run that. So it is possible to write directly to NVMe, although you probably would want to do that the same way you go through a file system to get to your device and not directly go to your device. Yeah. Any other questions? I had some candy I was supposed to give out for all good questions, so there's still lots of candy. Okay, one. Hi.
Yeah, maybe as a follow-up. Is it NVMe specific in any way or completely decoupled? And is it specified how these high-level APIs are mapped on, say, NVMe?
Okay, good question. So is there a specification or something of that nature that maps the APIs to NVMe? So we didn't do that exercise specifically, but they do map pretty well. I can say that for sure. Yeah. As you can see, I touched on the memory, I touched on functions, downloading, execution. So you have the same concepts that are there on NVMe side. And some of the folks who worked on the SNIA side influenced the NVMe side and vice versa. Yeah. So yeah, it was a closed loop to get things to match each other. And we did work as standard bodies to closely together. And there was good feedback both ways, yeah. Okay, there's one more question.
Is the idea that SNIA itself will develop the high-level SNIA Computational Storage library, and then the vendors would provide plugins?
Okay, so will SNIA develop a computational storage vendor library or a library, or is it up to the vendors to develop? Right? That's what you asked?
Oh,
yeah. Okay. Yeah. So we are 0.9. So once we are 1.0, let's hear back from the board on what are the next steps. I think that has not been discussed, but I think that would be the very next step, because if I have to give an update here, even on the NVMe side, we are completing computational storage. So once that is complete, the next logical step would be to develop software for the device, and the same thing may apply to SNIA, but I will leave that once it is standardized. Yeah. Any last questions? All right, so I can give you back your 20 minutes. So, thank you, everyone. Thanks for attending.